Okay, so in the last video, we discussed the three types of nuclear radiation that can come out of a nucleus releasing energy: alpha, beta, and gamma rays. Let's talk a little bit how we'd go about detecting them. So probably the most straightforward way of detecting radiation is to do something like this. You would get a tube, could be glass or metal or something, but something that can sort of give you some volume to work with here. And what you do with the tube is you'd put an electrode right down the center of the tube like this. You could sort of maybe have some electrical access to the outside, not that hard to do. And what you would do with the tube is you would bias it up to something like maybe about 600 volts or something like that. Get some sort of high voltage power supply, bias like that, ground it relative to the case, something like that. And so you have this electrode sitting inside this casing here that's biased at 600 volts. And then what you do is you put some gas inside of here. Maybe I'll just sort of draw it in this pinkish color here. And what this gas could be here is maybe something like neon or argon or something like that would go in there. Okay, so here's what happens, how the detection could possibly work. So what will happen in this case here is, suppose an alpha particle came along. And remember, for alpha particles, they're stopped by a piece of paper, so you'll have to be a little bit careful about what you make the face of your detector out of if you want to detect alpha particles. But there are some elements, I think something like mica. If the face of the detector is made out of mica, then an alpha particle can pass through. But again, you have to be careful with these kind of things, because if you want to detect alphas, you don't want your detector itself to be blocking them. But okay, let's say one way or the other, an alpha particle can sort of make it into this detector here. Again, it's all sealed off, but if the alpha particle can pass through the front face, and it can get in this area here where you have the high voltage and the gas. And so what will happen is the alpha particle will come in like this, and when it sort of zings through the area like this, what it'll do, it'll start to ionize, say, the neon gas in there. So I'll sort of draw the ionization maybe with some little plus signs and little minus signs as it sort of rips through it, ionizes like that. Okay, so what happens now is when you sort of have this trail of charge forming right here, then suddenly the 600 volts that's sort of biasing the conductor in there, say it's positive, will start to attract all these electrons. So all these electrons will sort of start to get pulled in by this positive electrode like this, and they'll literally just slam into this electrode right here. And when they do that, a little surge of current will start to happen on this electrode right here, because suddenly all these electrons are hitting this piece of metal in here. So there'll be a little current surge in here. I'm not quite sure exactly how to draw it like this, but maybe I'll just zoom and say sort of in this wire here, you'll get a little current. And it turns out that's not really that difficult to pick up sort of in a laboratory experiment kind of way. Like one thing you could do, for example, here is you want to protect your instruments from the 600 volts. So maybe you could put like a capacitor on here, something to capacitively couple to this wire here. And this could just sort of go out maybe to something like a little meter that has a needle on it, maybe a scale like that. And so what will happen is that when the ionization electrons from the alpha particles zinging through the gas start slamming into this conductor down here, they'll cause a little current to happen, which may cause different charge states on this capacitor to happen, and you'll get this needle maybe to make it start moving just a little bit. And so that would be the detection of a particle, in this case an alpha particle. And one of the probably the most popular things to do in this capacitive coupling, say, isn't maybe to put a needle on there like that. So let me just maybe erase this meter for a minute, but you certainly could see the needle jumping around every time a particle came in. But what you could do is just connect it directly to a speaker like this. So here's sort of the speaker cone that goes out like that, and maybe this goes to ground here, something like that. And what will happen is you can hear this current slamming into the electrode in terms of little clicks. And so that's where, click, 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 click. And so you've probably seen that in movies or maybe some other class you took, but that's where the click, click, tick, click, click, click of something called a Geiger tube comes from. And that's exactly what this is. This is what a Geiger tube is. It's the 600 volts, the gas, the evacuated area, and some way of letting the alpha particles come in. And so when this current happens on the conductor in here, you hear the click, click, click noise go off. And just a quick look again at maybe a better graphic here than certainly something I can draw would be something like this. So you can just sort of see it has all the elements I sort of showed you here. Here's that conducting rod inside that's charged up to 600 volts. Here's the casing right here. Here's the gas that's in there. And when the ionizing radiation comes in, say like an alpha particle, it starts to rip charge off of these atoms here, and you can start getting the click. They even have a speaker in here, or you might have it connected, excuse me, to a scaler that'll actually tell you how many alpha particles, for example, per second have come into your detector. These are also good for beta particles. So we say an alpha or beta particle is nicely detected by a Geiger tube, but the gamma rays not so much. It turns out the Geiger tubes are very, very inefficient for gamma rays for the reasons that we discussed. So if a gamma ray does come in, the odds are what the gamma ray is going to do is just pass right through the detector, because these gamma rays are highly penetrating. However, what can happen sometimes, they're not like they're totally blind to gamma rays. What can happen is the gamma ray can come in, and when it encounters the metal literally of the case here of the Geiger tube, then electrons can possibly be ejected from this metal here, and there's your charge right there. So when you get the charge like this, then suddenly they can be attracted down to this conductor here, and the same sort of process can happen that would generate the click. So they're just very inefficient for gamma rays, so we don't like using them. We don't like using Geiger tubes to detect gamma rays because of this inefficiency for just the gamma rays. Like, it just takes forever to get your data, and it's just kind of unreliable and all that sort of thing. And then the last thing that's sort of a bummer about the Geiger tubes is that when all of this ionization, let's just say, whatever you want to call this ionization packet or something, occurs, and there are all these charges in here, it takes sort of like a little delta T, a little time to clear. So when you get all this ionization happening that goes into generating the click, the ionization kind of hangs around for a while, maybe, I don't know, 10 microseconds or something like that. And during that time, the Geiger tube is unable to detect more particles. So if something really rips through here, like an alpha particle, and generates all of these charges in here, the Geiger counter, Geiger tube, is unable to detect subsequent alpha particles because it's sort of busy clearing this plasma in here, and that's sometimes called the dead time of the detector. So that's another reason why we sort of try to get away from them in some of our labs, is because the dead time sort of reports an artificially low number of counts while the Geiger tube is recovering from the previous event. So anyway, that's sort of the story then on some real basic detection. And these Geiger tubes, you can buy them for about $120 or so, and you can make your own if you want. They're kind of nice. They'll click and do the things. But we still have this question among us here: what do we do for the gamma rays? Okay, so the Geiger is perfectly sufficient for something like an alpha or beta particle that's going to cause this ionization of the gas, but what about the gamma rays that would pass right through? That'll be the topic of my next video.